Hi, I want to run through some more examples of finding trig values of special angles in radian mode. So the first method I'm going to use is one that is probably exactly what Khan Academy shows, although they may start with a blank unit circle. I'm going to kind of jumpstart this since you've now no doubt seen the unit circle and probably tried it a few different times. The thing to remember about the unit circle that's really nice is if you have it memorized or in front of you and you can get to it quickly, all you really need to remember about it is what I call kind of the key to the map or the legend to the map. It says if you want to know a sine value at any of these angles that you can find on, we call these all special angles because they're all increments of either 30 or 45. So that includes 60, of course, because that's a multiple of 30. But in radians, I guess I'd be saying pi sixths, pi thirds, pi fourths, that kind of thing. All right, so if you know your angle, then you can find the sine value of that angle by just locating, for sine, it would be the y value of the coordinate where that terminal edge comes to a stop on the circle. So I'll show this in action in just a sec. And then for cosine, that's just going to be that value adjacent over hypotenuse is going to be found as the x value of the coordinate. So when I say x and y, I'm just talking about any of these coordinates here. Here's x. Maybe I'll quit switching colors. It takes too long. And there's y. So with this problem here, I was sent by a student. If you want to find the cosine of 3 pi fourths, first thing you got to do is locate the angle. So where is 3 pi fourths? And again, if you have this memorized and you're used to counting in radians, that's one thing. But if you got to kind of think through and develop the unit circle, I like to start with what fraction of pi am I talking about? And so if I can remember, this is the easiest radian fact I can remember, is that pi is the straight angle. Pi radians is 180 degrees. Okay, so if I can cut that angle graphic into quarters, so 1 pi quarter, 2 pi quarter, 3 pi quarter, 4 pi quarters, which would reduce to just 1 pi. So in doing that, we can count right to 3 pi quarters, which is going to be in the second quadrant. And obviously this unit circle is already labeled, so there it is. And we've got our x and y coordinates at that location. Now the reason, if you haven't caught on to this yet, the unit circle is called the unit circle is because the radius or the hypotenuse of all these reference triangles, no matter which angle you land on, you can always draw at the reference triangle that connects down to the x-axis. Never the y-axis, always the x-axis. All right, so the x coordinate is this value from here to here. It's this base leg, which if you're standing at the reference angle is that leg adjacent, and your hypotenuse is 1. So negative root 2 over 2 divided by 1 is negative root 2 over 2. Okay, now since this next problem is already obviously at the same angle location, all we're going to do here is use, because it's sine, remember, we got to go with the y value. So here the y value, very similar, although y is positive in quadrant 2. So instead of negative root 2 over 2, it is positive root 2 over 2. So when they say express your answers exactly, you can get away with these answers. In my next, on the next page, I want to show a different method. And there's actually an equivalent answer to what we just got here that's also considered exact. So let me switch the page. Oh, one more thing. If you ever are asked about tangent, let me complete the little key to the map here, so to speak. Tangent is, and this requires a little bit of reducing sometimes, but it's simply y divided by x. So if you know the coordinate, you can kind of reduce what y over x would be using the x and y pieces. All right, let's go to the next page. I'm going to work the exact same two problems hold on here, but with a different method. Okay, and this method I tend to like more, if I'm honest with you. And if we were in person together doing this and not in distance learning, I would probably see more people jump into using this than the unit circle. Although the unit circle is a beaut. It is a real good method. The thing I like about this one is you only have to memorize the two special right triangles and then remember how the XY coordinate plane works. And by that I mean, hey, this is the y-axis. Why is it not? I feel like the computer can sense my sarcasm sometimes and it stops working. And it's negative x values here, positive x values here. I mean, we've been doing this for a while, so we know how the coordinate plane works. We know where the quadrants are and what that means for the sign values of the different x and y pieces. For example, if you're at a point in the third quadrant, you know both x and y values are going to be negative. But if you're in the fourth quadrant, you're going to have positive x and negative y's. So I'm getting a little bit ahead of myself here. Step one is kind of like what we ran into with the unit circle. You have to identify where the angle is. So start by drawing a pi. A pi angle right here is one of the easiest things to start with. We know that 180 degrees and pi radians gets you the straight angle. All right. 2 pi would get me all the way around. But what we've got here is not just pi. Take it one step at a time. We have pi in terms of fourths. Okay. So again, and I kind of counted this out on the unit circle, but if I can cut this pi arc into equal steps, 4 equal steps, okay, with the last one being right at the end of pi. So 1 pi quarter, 2 pi quarter, 3 pi quarter, 4 pi quarter. Okay, 4 pi quarter is just pi. So look at the bottom, and that tells you how many steps to break pi up into. Now, the last thing you do is you take that many steps. So I wrote out 4 pi, or I'm sorry, pi in terms of fourths. And now I go, okay, this angle would be 1 pi quarter. This angle would be 2 pi quarters. This angle right here, oh, I kind of missed it. It's hard to be a perfectionist with this stylus. There we go, is 3 pi quarters. Okay, so we know we're in the second quadrant with this angle. And like I said before, you always want to drop your line from the terminal edge down to the x-axis. Okay. Now, earlier I said all you got to memorize is the two special right triangles. So in middle school, for a lot of you, or geometry, whenever that was, I guess some of you took that in middle school, or ninth grade, we learned them as the 45, 45, 90s and the 30, 60, 90s. Okay. I learned them as 1, 1, and root 2. A lot of other folks learned it as A, and A root 2, just to kind of get a ratio. Okay. But because we're in radians, I'm going to morph this, just kind of convert it. Gosh, my triangle drawing skills have gotten weak. And I'm going to say, instead of 45 degrees, that's a pi quarter angles here and up here. That's exactly the same. It's kind of like saying 2.54 centimeters is an inch. It's just, different unit of angle measure. So 1, 1, and root 2. So if you can remember your 45, 45, 90 in radians and go, oh, each of these little chunks here, as I stepped, were 45 degree angles, or pi quarters. Okay, so I know my reference angle that I'm standing at right here in the second quadrant is just a 45 degree angle. Since it's a right triangle, I know that also is going to be 45 degrees. So even though it doesn't look perfectly isosceles here, I know that these two sides are going to have the same length, and I'm going to get a root 2 for the hypotenuse. Isn't that slick? The thing you have to remember, I think I'll go to purple for this part, is because we're in quadrant 2, I know that the x's are negative and the y's are positive. Okay? Again, to the left here is negative. So I got to make this adjacent edge negative, and I'm going to leave this one as a positive. Now, hypotenuse, until further notice, probably late in the year pre-calc, the hypotenuse is always going to be a positive number. Okay, we'll explore something down the road called polar coordinates, and that's a different day. But for this course and for the foreseeable future, your hypotenuse is always going to be a positive value. All right, so if we know the 3 edge lengths of the special right triangle that we landed on in quadrant 2, and we can adjust the signs on the 2 legs to be signed properly, then we could very quickly just do the Sohcahtoa. Okay, so cosine we know is adjacent over hypotenuse from the Sohcahtoa, and I'm just going to stand in that reference angle corner here and go adjacent over hypotenuse. So that's -1 over root 2. Now, this is a fully acceptable answer. It's considered reduced and exact. There are professors and teachers and textbooks out there that never want to see a radical downstairs, and I'm not one of them. And I would say I'm starting to see it's more 50-50. It just depends what teacher or what school you're at, whether they want to see that rationalized denominator. So if the teacher you have someday is only using unit circle, you're going to have to multiply your answer here by the radical of that denominator in a super 1 formation. And that'll give you that very familiar looking negative rad 2 over, okay, that's just going to be 2, which is what we got on the first method. I am fine with this, and I believe Khan Academy will accept it as well. So just be careful when you punch it in. Since we already have the triangle drawn, we could do the sine value very quick. This is our opposite leg, again standing at our reference angle here, and you would get +1, +1 over root 2. And again, if you had that curriculum down the road or that teacher that does not want to see radicals in the denominator, it's not a big deal in the trigonometry unit for us to run into that. As long as the radical's reduced. You know, radical 2, you can't factor any other perfect squares out of it. So I am happy as can be with that value. So positive rad 2 over 2. Okay, so we do get the same answers if we rationalize the denominator, but we're good to go here and here as well in my book. I hope that helps. Keep working hard. Thanks.